Okay, now we get to the main event, which is solving right triangles, which I always thought was a funny sounding phrase, but what it means is solving for anything you want in a right triangle. Hey, how big is this side? Hey, what's that angle? And so on. Just solving for whatever you want in a right triangle. Now, the first thing you're going to need to do is you're going to need to remember which way is the sine, which way is the cosine, which way is the tangent. Remember we were drawing little arrows in the last homework. Now, actually, it depends on where your point of view is, so it looks like I forgot to throw a theta in there. Let's make that our point of view. That's the theta we're talking about. The sine, cosine, tangent are all associated with that particular angle, which has to be in a right triangle, by the way. Never forget that. It has to be a right triangle for this to work. But if you have a right triangle, and you have a point of view, theta, right there, then you can determine sine, cosine, and tangent ratios. Ratios of two sides. Sine is this side over that side. So let me ask you, which side over which side? Can you remember? Well, I remember it this way. I remember that I reach through to the opposite side of the triangle, and then I cross over the hypotenuse. That's the sine. And you might remember cosine is kind of a toni, cosine, right there by my chin, but over the hypotenuse. So this was the sine of the angle theta. This was the cosine of the angle theta. And then the tangent, if you're not careful, will hit you in the face. The tangent is the only one that doesn't do the hypotenuse at all. It's opposite over hypotenuse. So I remember those just kind of spatially. And if you don't remember them spatially, that's fine, because there's something you can always fall back on, and that's the old soh-cah-toa, right? Remember that? Soh-cah-toa, where this SOH is telling you that sine is opposite over hypotenuse. So you take the opposite side and put it over the hypotenuse side. So what are we talking about? Well, we know that's the hypotenuse side. And remember how you find the opposite. You walk through the triangle to the other side, way over here. That's the opposite side. And then this, by process of elimination, is the adjacent side. You can also say, well, I'm kind of standing on it. I'm right next to it. I'm right next to the adjacent side. And so you'll notice that for the sine, I did indeed go opposite over hypotenuse to get the sine. Cosine is an AH, adjacent over hypotenuse, and that's why we went from the adjacent over the hypotenuse. That's the cosine arrow. And then tangent is a TOA, is an OA. T is OA, opposite over adjacent, and that's why I crossed from the opposite over to the adjacent this way. Okay, so those are our three arrows. Now, always remember, it's not the arrow itself that's the sine. When I say the sine of that angle, what I mean is, when I draw the arrow opposite of hypotenuse, what I actually mean is, take the length of this side, which is some number you can measure, take the length of this side, which is some number you can measure, and put one over the other. Actually put one number over the other. Make a fraction, or if you want, divide and make a decimal. And what you had to do in the old days is you had to figure out for any angle you wanted, and let's just focus on the angles 56 degrees, 57 degrees, 58 degrees, or whatever. You would have to actually build yourself a triangle that had the 56-degree angle, maybe make it in the machine shop, I don't know. And then you would have to measure all the sides of that triangle, and then you would have to do the division like I was doing up here. And back then, when you had the answer, you'd write it down so you didn't have to do it again. Or maybe write it down so that somebody else doesn't have to do it or something. Or write it down so you can sell the trig table to somebody. That's probably what it did, right? That's what they did. And then you'd build your thing, and you'd have a 56-degree angle, and you'd measure the adjacent and the hypotenuse, and you'd put a ratio together, and you would get that the cosine was 0.559, and then you would do the same thing for the tangent. You would build your triangle, you would measure the opposite and the adjacent sides, you would take the ratio, and then you would write it down, and if you went to 3 decimal places, it would be something like 1.483, something like that. And then you'd do the same for a 57-degree. You'd build another triangle. It would be 57 degrees. You'd have to build it. Then you'd have to take the dimensions. Then you'd have to divide them, and so on. And this is going to be a little bit bigger now, 0.839. And that's because if you go from a 56-degree to a 57-degree, the sides, this side's getting a little taller. guess the hypotenuse is maybe, oh, is it getting bigger? I don't know. No, just keep this dimension the same. If you keep the hypotenuse the same, then yeah, it's getting taller, so the sign's going to have to be a little bit bigger. And it is. And you would measure this and so on and go 0.545, and then you would measure the tangent of the 57-degree triangle, and you would measure 1.540 or something. And then you could build another triangle at 58 degrees, and you could take this, make the measurements and so on, write down your results, take the ratios, write down your results in a nice table. So I'm just finishing this table for us here. So we'll at least have information for 3 different angles. That's kind of nice. That'd be a 0.530. And then over here, what do we got? It takes a long time to make and build and measure, you know. Give me some time, will you? So this is like a 1.600. Okay, cool. We're just going to use that table for the next 2 examples in part B here. But just looking at it, notice the sine kept getting bigger, 0.829, 0.839, 0.848. The cosine kept getting smaller, 0.559, 0.545, 0.530. So as the sine gets bigger, the cosine gets smaller. That tends to be a general truth of life. Anywho, let's use that table now to solve for x. Part B here says using trig tables to solve right triangles. Okay, we can use that table. The whole question is, which of these numbers are we supposed to look up? Well, I suppose if we're playing with a 57-degree angle, we must be playing with this row of our table, right? So there's 3 numbers. 0.839, 0.545, 1.540. One's the sine, one's the cosine, one's the tangent. Okay, next question. For this triangle over here, let's use a different color now. For this triangle over here, which trig function do we want to use? Well, notice I got a 57-degree angle, so that's like my point of view, that's my theta. And I want x, and I have 52, so I want to cross the triangle this way. And then you say, well, let's see now here. If I had crossed the triangle like a etoni, this would be a cosine, right? That is a cosine, because that's a hypotenuse. And I'm standing on the adjacent. This is the adjacent, this is the hypotenuse. This is one of those CAH situations. So we're using a cosine. So this is a formula. This says that the cosine of theta is the adjacent over the hypotenuse. That's the formula that reminds us of. CAH is that formula. And then what you do is you say, well, the theta that we're talking about here is 57 degrees. So the cosine of 57 degrees is, and the adjacent that I have here is, well, it's x. And then the hypotenuse that I have here is, well, it's 52. And notice I got a nice little equation here that I can basically solve for x. I find what people are usually comfortable doing is finding this first. So you can come up to your table here and you can say, oh, the cosine of 57, there it is. It's a 0.545. And so 0.545 is equal to x over 52. Now, how do you get x by itself? Well, there's 2 ways you could look at this. You could look at this as I need to, creepers. You can look at this as, oh, for heaven's sakes. There we go. You can say, well, what I'd like to do is I'd like to multiply both sides by 52. Because this says divide by 52. This is the opposite, which is multiplying by 52. If you multiply both sides by 52, you'll have x is equal to 0.545 times 52 is equal to something. 0.545 times 52 equals, it's just about 28.34. Roughly. 28.34. So like I was saying, that's one way you could have done it. The other way you could have done it is you could have like kind of sort of like thought of this as a proportion. Put this over 1 and do cross products. 1x equals 52 times the cosine of 57. 52 times the cosine of 57. So if you want to look at it as a proportion that happens to have a 1 underneath over there, well, that works too. Okay, so yay, we actually figured out how long that side was. This side happens to be 28.34. Because of the good old trig tables that somebody worked so hard to make for us. Wasn't that nice of them? I love it when people do nice things like that, and then they hand it down to future generations. It's great. It's just great. Let's see. You want to think about this triangle over here? So the situation is the same. We've got an angle, so this is like our point of view. It's kind of like we're standing over here. Mr. Theta Head is standing over here. And, well, we got this side, and we want this side, so we're going to cross the triangle. I don't know if we're going to go this way or if we're going to go this way, but we're obviously going to use those two sides. And so ask yourself, what kind of trig function is that? There's a tangent here somehow. One way you can remember tangent is it doesn't involve the hypotenuse. If we're not using the hypotenuse, we're using a tangent. Of course, you could also do it the other way and say, well, you know, here's my hypotenuse. And if I go through the triangle all the way to the opposite side, then that's the opposite side. And also, I'm kind of standing on my adjacent side here. So notice we're playing with opposite and adjacent, OA. And so you can ask yourself, which of those soh-cah-toa things has an O and an A? It's the tangent. The tangent has an O and an A. So that's the tangent. That's the one that will hit you in the face if you're not careful. Opposite over adjacent, that way. That's the tangent. So again, remember, TOA actually is a little shortcut way of writing out a formula that says tangent of theta is opposite over adjacent. And now we can actually plug into that formula. The angle that we're playing with here is 57 degrees. That goes there. So tangent of 57 degrees. The opposite is 52, it looks like. And then the adjacent is x. So there's where the x goes. So the x is on the bottom this time. It happens. So how about we just go get the tangent of 57 right now. So I'm going back up to my table. Tangent 57. That's a 1.540. Okay, cool. 1.540 equals 52 over x. Now you're going to solve that one. I suppose you could multiply both sides by x. I actually don't like to look at it that way. I mean, you can, but I don't like to. I really like to look at this one as a proportion. That makes it easier for me. Because then I can say, oh, okay, cross products then. Remember, you can always stick a 1 underneath anything. 5 over 1 is the same thing, right? And you can always stick a 1 underneath. So if I stick the 1 underneath, all of a sudden it looks like a proportion. All of a sudden I can do cross products. 1.540x is on this diagonal. 1 times 52 is on this diagonal. And that means I'm dividing both sides by the 1.540 like this. Right? You want to cancel off the coefficient of x. 52 divided by 1.54. What do we got here? 52 divided by 1.54. We're getting like, if I use a couple decimal places, it'll be 33.77. 33.77. That's about what this is. Now, isn't this fun? Now, before we go to the next page, I got a challenge for you. I want you to go build a triangle real quick. Go to the machine shop, get the milling machine out, build a triangle that has, it's a right triangle, one of the angles is 90, and make another angle 59, and then measure the sides and figure out the sine, cosine, tangent. Okay, obviously nobody did that. Here's what you can do these days. Get out your calculator and press, there's a little button that has an SIN on it. It's kind of in the upperish part, kind of in the middle-ish part. You can't really miss it. It's right there. See, it's right there. SIN, sine. Press the sine button and then press the 59. So I'm going to go sine button 59. It opens up a parentheses. If you want to be careful about it, you'll close your parentheses. It opens up a parentheses for you. You put the 59 in there, then you close the parentheses, and then you hit your equals. And it tells you it's 0.85716730007. So to 3 decimal places, it's 0.857. Ain't that something? Basically, somebody already made this table, and they put the table in the calculator for you so that you can get these things just by asking your calculator. So let's say you wanted the cosine of 59 degrees, and you said, hey, what is that? well, you can go build your triangle, or you can use the cosine button. So you hit the cosine button, and your calculator will give you a cosine with an open parentheses. It's saying, hey, give me an angle. So you put a 59 in. I'm going to close the parentheses to be careful. Hit equals, and this time I got a 0.515. 0380749, but 0.515 is accurate to 3 decimal places. Notice it seems to be in the right trend, right? These kept going up. It went up a little bit more. These kept going down, went down a little bit more. It's the right trend. It's got to be right. It's electronics. It's got to be right. How can it not be right? It's got to be. And then if you wanted the tangent, guess what? You'd hit the tangent button. So notice these 3 buttons are all right next to each other. Sine, cosine, tangent, all across the, what would that be? Depending how you count. You might say that's the 4th row from the top. You might, if you include the blue buttons. If you don't, you might say it's the 3rd row down from the top. Something like that. Anyway, sine, cosine, tangent. So you hit the tangent button. Then it wants an angle, so I put the 559 in, close it. 1.664 is what I got here. Ain't that something? So obviously you can plug in any angle you want. You can plug in 59.125 degrees. And it'll give you the accurate answers for sine, cosine, and tangent. It's an amazing thing. So, okay, knowing that we don't actually need a trig table, which is why I know I'm never going to get one ever. No one's ever going to find one at a yard sale. Sigh. They used to make them out of like this real high quality, like almost like leather. Probably not leather. It was probably vinyl, but oh, they were so good. Anyway, next page. Okay, all together now. We got 3 tools for solving right triangles. What I just showed you doesn't actually count as 3 tools. Sine, cosine, tangent to me is all the same tool. It's the soh-cah-toa tool, and that's one of your 3 tools. Soh-cah-toa. That's one of the 3 things you can use to solve right triangles. But don't forget, there's other things you can use too. Remember that thing called Pythagorean theorem? That's another tool that will come in handy sometimes. Let's remember how that goes. As long as you have a right triangle, then let's call these 2 sides A, B, and we'll call this side C. I have an idea. This has never been done before in history, which of course has to be wrong. There's too many people out here. But I'm going to call this H. You know why? Because that's the hypotenuse. So the Pythagorean theorem says when you take the a squared plus the b squared, it equals the hypotenuse squared. Now, why do people not put an h there? That would make it so much easier. I say that because the main thing about this formula is you must make sure the hypotenuse is on the right. That's the hypotenuse. Okay, you get 3 numbers to play with, of course. Does it matter where you put them in the formula? Heck yeah, it matters. The hypotenuse has to be the one that's over there. Okay, so I think I'm just going to put an h there. That looks good to me. Okay, so a squared plus b squared equals h squared. So let's maybe throw a little example here. Sheesh, keep forgetting to change my tools here. Let's say this side was a, I don't know, 3 and this side was a 4, and I want to find the hypotenuse, which I called it x, but you know it's the hypotenuse, right? I'm going to call it h. Well, a squared plus b squared. Actually, which one's a and which one's b doesn't matter. You can switch those back and forth. That doesn't matter. What matters, again, is that you get the hypotenuse, right? So maybe I'll erase the a and the b. The point is I got a 3 squared and a 4 squared equals my hypotenuse squared. Now to solve this equation, you got to make sure, some people, I've seen it done. Don't let this be you. Do not do this. Do not say, oh, I'll just keep taking square roots all the way across. And so I've got 3 plus 4 equals h. So h must be 7. It doesn't work that way. You can't take square roots one at a time like that. What you have to do is you'd have to take the square root of everything. Okay? So in other words, what you'd have to do is you'd have to take the 3 squared, which is a 9, the 4 squared, which is a 16. You'd have to add them up first to get a 25. And then you take the square root of 25. Okay. Why are we taking the square root of h squared? Because we want just h. But again, like I say, you want h squared. You got h squared, you want h, you need to take the square root. Please don't just do it a term at a time. That makes things messy. Now let me get this out of the way. And let me, I'll keep the formula here, but let me change this triangle a little bit. That's going to be the hypotenuse, of course. But let's say this time we knew that this was a 5 and this was a, I don't know, 2, just to make something up. And we wanted to know what this side was. Well, we're going to use the same formula. Get that out of the way. Get out of the way. Get out of the way. We're going to use this same formula up here, but this time, notice that the 5, since it's the hypotenuse, it has to go over there. So I've got 2 squared plus my x squared equals my 5 squared. Very different, okay? Very different, because now the x is on the left instead of on the right. So again, you're not going to be doing this kind of stuff, right? No, you promised me. Don't do that. What you want to do instead is first do all your squaring. 4 plus x squared equals 25. Then you want to get x squared by itself, which means subtract 4 on both sides. And the very last thing you do is you get out your square root button, and you do it this way, okay? So 21, square root of 21, my calculator's telling me that that's about 4.58 or something. Okay, so I'm just showing you to be very careful with this Pythag theorem. Make sure hypotenuse on this side. Hypotenuse goes on that side, okay? Whenever you use the Pythagorean theorem. I guess, looking at this a little more carefully, I guess where I usually see people make mistakes is from here, they'll say x squared equals, and they're subtracting 4 on both sides, and they'll actually write it out. And then they'll make this mistake, and they'll say, well, I'll take the square root of this, I'll take the square root of this, I'll take the square root of this. Right? But that doesn't work. Again, that doesn't work to do it that way. That gets you the wrong answer, for one thing. You have to actually subtract first. Then you can take the square root. Okay, so just be very careful using your Pythag theorem. We will, of course, get a lot more practice with this stuff. Let me use some scissors here. Delete me. Okay, so that's a good enough statement of the Pythagorean theorem, I think. A squared plus b squared equals c squared, except I'm going to say h squared because it's very important that the hypotenuse is on the right. Very, very important. Okay. There's a third tool you can use, which is actually really nifty and really short. If I told you that this angle here, just to make something up, if I told you that this angle here was 30 degrees, could you figure out what that angle is? That's supposed to be a theta. What would be that angle? 2 ways you can do it. One way you can do it is you can say, well, all the angles of a triangle have to add up to 180. So you could say, you know, I got 30 plus 90 makes 120. So if I'm going to add up to 180, that would have to be 60. Exclamation point. Or if you don't want to get that involved, just skip the 90. What is the 90? 180 degrees are in a triangle, and that's 90 of them. That leaves you 90, right? So the way I like to do this is I like to say the 2 acute angles, which means sharp angles, sum to 90 degrees. In a right triangle, I suppose I should be careful here, in a right triangle, the 2 acute angles, again, acute is sharp. You ever have an acute pain? Ow! It's like a sharp pain. Ow! These are the acute angles. They're the sharp ones. This one's not so sharp. That's dull. So the 2 sharp angles, the 2 acute angles, add to 90. So if that's 30, you just say 30 plus what is 90? Oh, 30 plus 60 is 90. That must be a 60-degree angle. These 3 tools together are what we use to solve right triangles. You'll notice that I have a couple examples here. Solve for everything that's missing. Okay. And we're going to use these 3 tools to do that. And typically, we'll use each tool once. We'll use the soh-cah-toa once. We'll use the Pythag theorem once. We'll use this once. We might not use all of them. Depends what they tell us. But you don't usually have to do soh-cah-toa more than once, I guess is the bottom line that's comforting to me. You don't have to use soh-cah-toa too many times on one of these things. So I'm looking at this triangle on the left here. And I'm asking, okay, what's missing? Well, nobody gave us this side. Nobody gave us this side. and nobody gave us this angle. I guess everything else is good, right? Yeah, we got the 24 degrees, we got the 17.4, so that's all we're really missing. We can do this right away, using that idea that the acute angles add to 90. So 24 plus what is 90? Well, let's see, just count out 24. 30, 40, 50, 60, 70, 80. So it could be 66 degrees. I don't need to put a theta there. I can just say, hey, that's 66 degrees. And then you can always spot check yourself. 66 plus 24 is 66. 76, 86, yep, that's 90. Good. See, we're making progress. 1 down, 2 to go. Now I'm going to solve for, yeah, I guess I'm going to solve for x next. Might as well go in order here. Alphabetical order, not that that's important, but might as well. So let's see, if I like to use the 24 degree angle because that's the one they gave me. So I'm going to start with the 24 and I'm going to say, okay, I've got this 17.4 and I've decided I'm going to solve for x. So it looks like I need to cross that triangle in this sort of a sense. Which trig function is that? Well, again, this would be, if this is me point of view, then this is me opposite side. You come through the triangle to get to the opposite side. That's the hypotenuse over there, so this is the adjacent. We've got opposite and adjacent. Soh-cah-toa, it's a tangent. OA is tangent. So what you do is you write this down. The tangent of 24 degrees is, and then the opposite side is 17.4, and you divide that by the adjacent side, which is x. Cool. So tangent of 24, well, you could look that up in a table if you want. You can push the buttons on your calculator if you want. And my calculator says that it's 0.44523. I like to actually use 5 sig figs when I'm in the middle of a calculation. 3 sig figs just doesn't quite do it. Your answer will be a little different than mine. 5 sig figs tends to be plenty. So 0.44523 is how I'm rounding that up, equals 17.4 over x. So remember this idea that you can actually think of this as over 1 and do cross products. And so the 0.44523 times x on this diagonal is equal to the 17.4 on this diagonal. And then my last step is to divide both sides by the 0.44523, 0.44523. 17.4 divided by 0.44523 is, I got myself an answer of 39 point, I'm going to go 0.8. Typically I go one more decimal place than they gave me. They gave me 1, I'll give them 2. Cool, we got a side. Let's erase this stuff. I don't need that anymore. Okay, I'm going to change my colors here so it's easier to keep track of what I'm doing now. Now what I'd like to do is solve for y, of course. I got that side, I got that side. And whenever you have 2 sides, in fact, let me put this down here so we'll have room for the other problem. So I'm going to say it this way. You got 2 sides. I should be a milk commercial. You got 2 sides, use Pythag. Pythag always works. And again, I'm going to write it this way, just a h squared. The hypotenuse has to go on the right. So I've got 2 sides, and I want the third. Notice Pythag is perfect for that. If you know any 2 of these, you'll be able to plug them in and get the third. Wonderful. So let's see now here. Which sides have I got? Well, it looks like the side that I want is the hypotenuse. The side that I want is the y. So the y squared goes over there. Take my other 2 sides. One of them was a 39.08. I'm going to square that. And the other one was a 17.4. I'm going to square that. Okay, so take my 39.08 and square it, and I'm getting like a lot. 1527.2464. And I add on to that a 17.4 squared. and I got like a 302.76. That equals y squared. So now I add those two numbers together. So the nice way to do this on a calculator, actually, if you don't want to have to keep writing all this stuff down, is you can just, on your own, write 39.08, or not write, but punch in 39.08, hit the square button, hit the plus, 17.4, hit the square button, hit the equals, and then hit the SD. And then you've got this, 1830.0064. Now that's what's showing on my calculator. I don't have to write that down necessarily, but you know what the idea is. The idea is to take the square root of both sides. So I just hit square root button, and then I hit the answer key. Nice shortcut. Square root of answer is. And here we have a nice result. Y is equal to about 42 point, was I going 2 decimal places? Yeah. 42.78. You want to round to 2 decimal places. Don't just stop at 2 decimal places. So rounding to 2 decimal places, I got 42.78. And we've done it. We've solved for all sides of this triangle. 42.78. We got that side, we got that side, we got that angle. Okay, so this would make a nice little exercise for you at the moment if you just pause the tape, so to speak, and try to solve this for yourself. Why don't I use, I'll call this like X and I'll call this like Y, and don't forget to solve for the angle as well. So if I call that X and Y and you call that X and Y, it'll be easier to follow what I do. But pause, try it yourself. You're back? Okay. First thing I'm going to do is I'm going to get that angle, because that's the easy part. 73 plus what is equal to 90? Let's see, 73, 83. I'd have to use a 17. So that's 17 degrees. We got 1 down, 2 to go. Now we have to solve for either X or Y. It doesn't matter which one you solve for first. I suppose I solved for X first last time. I might as well try to solve for X first this time. What the heck, right? So here's the angle that they gave me. I always work with that one. And I know this, and I'll just get X first. I could get Y first, it doesn't matter, but I'll get X first. And so I have to ask myself, which trig function is it that involves these two sides, and also which way am I supposed to walk across the two sides? That's important too. And you have to say, well, it's either soh-cah-toa, so let's see now here. Or you can remember Tony. If you're not remembering Tony, then you'd have to say, well, that's the hypotenuse. I would come through the triangle to get the opposite. Yep. I'm standing on the adjacent. Yep. So I'm talking about adjacent and hypotenuse here. AH. So is it SAH? No, it's SOH. Soh-cah-toa. Soh-cah. It's a C. It's a cosine situation. So the cosine of theta is equal to the adjacent over the hypotenuse. In this situation, what we're saying is the cosine of 73 degrees is equal to X over 947. Oh, that's cool. Cosine of 73, I can look that up as a decimal if I want. Maybe I don't want to. 1x equals, I'm just going to write this down. 947 is going to multiply the cosine of 73 degrees. There, see, that way I don't have to write it down. So I go 947, and I just hit the cosine right away. The calculator knows that I mean multiply. So 947, cosine button, 73, close parentheses, equals, bada boom, bada bing, x is 276.88. That's this side. 276.88. Woohoo! Now, how are we going to get that? How are we going to get this side, the y? You could do soh-cah-toa again if you really want to. I think it's quicker to do a quick Pythag. Remember, as soon as you have two sides, you're ready for Pythag action. So write down Pythag. A squared plus b squared equals hypotenuse squared. And the hypotenuse is right there. It's the 947. So that's what's going to go over here. The side that I know is 276.88. And the side that I don't know, I might as well just, well, it's a y. I might as well call it what it is the y squared. There we go. Now, obviously, it wouldn't matter if I put the y on the left or the right here because I'm just adding, and you can add things in any order and everything's fine, right? But it is important, oh so important, that the hypotenuse is on the right. Always make sure your hypotenuse is on the right. Okay, Now I want to solve this thing. So I'm going to write stuff down like this. Notice first you'd want to subtract both sides, right? Take this, that's SBS for subtract both sides. So that would get me y squared equals 947 squared minus 276.88 squared. Okay, and then to get y by itself, I would have to take the square roots. But remember, you're taking the square root of what you get after you subtract. You have to take the square root of like all that stuff after it's been done. So that's what it looks like. And if you want, you can enter it just like that on your calculator. You can hit the square root button, you can hit the 947 button, and then you can hit the square button, and then you can minus, then you hit the minus, and then put in 276.88, hit the square button again, and you should be able to just hit equals, and there you go. 905, and if I round to 2 decimal places, this will be a 62. 905.62. And it's not a bad idea to just kind of spot check in the end. I got an answer here that's less than the hypotenuse. That's good. I always like when that happens. If you got an answer over here of something like, 1,050 or whatever, you'd have to say, no, that side's not bigger than the hypotenuse. It can't be. The hypotenuse is the big side. So, you can just spot check sometimes, and you'll catch some of your mistakes that way. But cool. Those are the 3 tools. So let me come back up here and summarize the 3 tools. You get your soh-cah-toa, which you usually only have to use once. You get your Pythag theorem, which you're usually only going to use once. And then you've got the sum of the acute angles adds to 90, which again, you're usually going to use once. 3 tools, boom, boom, boom. If somebody gives you a little bit of information about right triangles, you may be able to figure everything else out using those tools. Cool.